Okay, so my talk is on designing flexible probes to explore the cellular changes induced by environmental enrichment and slow wave sleep. And so here's where we got our environmental enrichment protocol from. This is Gaddis et al. 2022. These are pictures of their tracks. We've kind of iterated on this a bunch, made it more automated, hands off. But the general idea is the same. We've got these tracks that some mice run around and they will encounter objects as they go around and they get rewarded for each lap. We use milk. And then there is a exercise control track that doesn't have any objects changing every 10 minutes. Their life is a lot more boring by comparison. They just get these ramps. In this training, we'll go on an hour a day, 5 days a week for a total of 9 weeks. And so we'd kind of done this before in the lab. I wanted to do it more in parallel. So me, a bunch of undergrads, and some high school students made the scientific term is a metric crud ton of these objects. We made quadruplets of everything, so we ended up having 320 of these little boards with objects on them. To also go more parallel, we made 6 new tracks for a total of 8. And to fit it all in one room in this ULAR provided space, I made these 4 double-decker tables out of wood that kind of roll around. And so being able to do it so parallel will help us collect significant N, and we need a lot because I will end up having 4 groups, not only the 2 I've introduced, the enrichment and then the exercise control, but we're going to double that. And the difference between those 2 sets are going to be this new group is going to get a bunch of slow wave sleep after the track training. We're going to induce that with a dread model, a dread mouse model. So how that would work is you take a VGAT-Cree, already slightly genetically modified mice, you put a virus and let it cook in a certain brain region. And then that will allow you, when you give them a drug, we give them DCZ, that will allow you to activate the receptor the virus is expressing. And then this specific subclass of neurons in this specific brain region in the brainstem, that will induce slow wave sleep. And so we're going to do that for 2 of our groups are going to get that every day after the track training. And you might be like, why are you doing this? That's a good question. This is a diagram showing the standard theory of memory consolidation. So you've got multiple memory systems in your brain. Here are 2 of them highlighted. We've got the hippocampus on the bottom. This is going to be a fast learner. It's fast, especially relative to the neocortex on the top. And so early on, your hippocampus will hold on to these memories and help you express certain types of memories when you first learn them. But eventually, you'll be able to consolidate that information, transfer it over into the neocortical cell assembly is what we'd call it, Hebbian cell assembly. And so you can see these are the same neocortical neurons that were firing during the first lived experience. But then the hippocampus, during slow wave sleep especially, the hippocampus will repeat this pattern multiple times to the neocortex, giving it an opportunity to actually make these connections you see later on. And so our hypothesis is, not a hypothesis, we know almost certainly, right, from decades of research that if you take these control mice and these enriched mice, you end up with a lot more memories in the cortex and a lot better behavior in the enriched mice. But our hypothesis on top of this is maybe the enriched mice getting a bunch of slow wave sleep after the training could even help consolidate the memories, have more neocortical memories. We could kind of make a super enriched mouse, so to speak. And so we're going to have all these cellular changes. Maybe they fit our theory, maybe they don't, but we need to look into the brain somehow and see what these changes are. And there we go. I modified these really flexible chronic probes that just came out last year. Somebody came back from a conference in our lab last year and showed me this paper, Yassar et al., 2024. And these just got me really excited. Everybody wants chronic, but it's really hard to do, and these guys did a good job. You can see their probe design here on the left. So this bit is where they solder directly to some computer chips. So this is not important, but at the bottom, you've got these 4 macro tentacles. And if you zoom into the tips of these, there are 64 individual, very fine and flexible wires. And those are very important properties for chronic probes. If you want to put something in the brain, it's really nice to be small and to move with the brain so you don't cause any more damage beyond insertion. And so to give you a hit, like just let you know how small these are, an individual wire here is, the big dimension is like 7 microns. It's like 7 microns wide. And the thickness of it is 2.5 microns. So even that big dimension is about 10 times smaller than the diameter of your hair. And with this technology, for 3 months in the rat, they were able to hold good recording quality and a bunch of units, neurons, in the cortex and the hippocampus. And this, I think I might have already said, this stuff is hard, doing chronic recordings, and I'm learning that myself now. I started editing their probe design to be optimized for the mouse cortex. And so this is my wafer I made with the help of the engineering department. And there's 50 individual probes on here. So that's a little over 3,000 wires, 3,000 channels that can go in the brain on a single wafer. Even with the first-time costs, we're looking at about $20 to manufacture one of these probes. And as you do more batches, that price will be even better. And so each, I can't remember if I said this, each one of these probes has 64 channels. Okay, so that's like a third of the battle. You've got something you can put in the brain, but you actually need a kind of an intermediate little bit of hardware, electronic hardware, that's going to plug into your probe, but also plug into your recording computer. And so this will measure, this head stage here in the middle and the left is commercially available from Intan, which is the recording system we already use in the lab. It's kind of expensive. It's $3,000, and it's kind of comically big. You can see it to scale with the mouse skull on the left. This bit of hardware will just measure the voltage on the wires and allow you to save it in a language your computer will understand. I was able to take their design and make my own on the right. This is, for my experimental purposes, this functionality is identical to what you can already buy from Intan, but it's 2.5 times smaller, 40% lighter, and a little less than half the cost. And another third of the equation is going to be this commutator design. So we want to do long recordings, and the next slide will explain why we want long recordings. But ideally, we put them in their home cage, let them chill out. We have a wire plugged into that head stage that's attached to their skull. And this commutator will allow us to leave them there with the wire being untwisted by this device. This device was open sourced in this paper here. I'm not even going to try to butcher those names. But this is really cool. God bless these people. I sent them a thank you letter after building this, because usually this bit of kit is like $5,000 to $10,000. And I was able to make this on a weekend following their very clear instructions for $168. So we could set up 2 of these in a giant Faraday cage. When you're measuring microvolts, even like the hum of the electricity in the room, you can pick up. So this Faraday cage will help. And then I'm not an expert at this part yet, but hopefully I can convey this succinctly. This will be like after I've collected my data and we're crunching the numbers. We'll use things like the extracellular trace down here on the left to identify, once we see a specific neuron over and over again, what type of neuron is it? Is it excitatory or inhibitory? And then once we have, you'd make these cross-correlograms to further figure out, okay, who's connected to who? And so let's say you take 2 neurons that you think are excitatory. This would further reinforce this idea. If your cross-correlogram looked like this, you have a noisy floor. So if this bump weren't here in any of these, you would probably say there's no synaptic connectivity. They don't have an influence on each other in this short duration that you'd expect for an actual synapse to be there. And then you get all these unique kind of pictures. So the more spikes we have, the better this picture becomes. So that's why we want such long recordings. And then we're going to, in particular, once we've identified what type of neurons we've got, who's connected to who, we're really interested in this type of connectivity motif, these excitatory pairs of neurons that are reciprocally connected to one another. And this comes from theoretical work that actually got the Nobel Prize in physics in 2024. This is John Hopfield, who made the Hopfield attractor artificial neural networks. And for decades, these have enforced a symmetry in their connectivity matrix or their weight matrix, which is just nerd speak for the diagram I just showed you. They enforce this mathematically, and these are one of the few bits of software where you can actually make the computer have memories and do pattern completion. And so if we can get that far and detect these types of connectivity motifs, these will be our analogs, our measuring sticks for cortical memories, for cortical Hebbian cell assemblies. And with all that preamble, this is our hypothesis going into this experiment. In the beginning, when we record from the mice, when they've all, like right before they've all started having different experience on the track, during the first week, it's all the same control ramps. They should all have the same amount of cortical memories. And then in the middle, after 4 weeks, we should see some differentiation, and then even more differentiation by the end. Dr. Saxena from our lab, who graduated this year, did a similar experiment without the slow wave sleep, and with a cube probe. So he got these 2 data points. But with the technology I'm trying to make, it'd be really cool to include all the red dots and also see this trend evolve over time. And with that, I'd like to thank everybody in my lab who's helped me and encouraged me. And a big thanks to my awesome undergrads who've enriched my life, and the RNRF department at the engineering side of campus. Questions? IE connections? Going off of the theoretical work, like the Hebb-Mar attractor networks, Hebb thought the IE connections, or maybe I should repeat the question. Let me repeat the question. When he's interested in IE connectivity, another type of motif, and following the theoretical work, you would expect increased amounts of that, which Dr. Saxena, I believe, is also seeing. The Hebb-Mar attractor network thinks that the inhibition plays a critical role in helping the right attractor network pop up, the right memory. And then your first question was, where do I want to record from? We're interested in replicating Dr. Saxena's findings. So just to keep it simple, any bit of higher order cortex will do, but this is where he roughly went in the retrosplenial and some motor cortex. That's where I'm going to aim for too. Thank you.